Hi, everyone. Let's get started this morning. Hey, thanks for being here. I just put in the chat a link to today's slides with the instructions and announcements that I'm going to go over, and also a link to where the notebooks are that our two delegate presenters are going to be showing. It's in the Delegate Contributions DP0.2 repo, so we're not using anything in your tutorial notebooks directory today. It's in a separate directory. I'm going to show you how to get that if you don't already have it. All right, today we're going to start with some announcements and setup. So if you haven't logged into the Rubin Science platform yet, go to data.lsst.cloud, choose the notebook aspect, leave the version at recommended, the weekly 40. Choose a large container today. I haven't looked at what the notebooks are going to be like, so just go ahead and choose a large container when you're not sure if you might need it. That's fine. We're going to be using notebooks that are in the Delegate Contributions DP0.2 repository. If you already have it, make sure you do a git pull to update your version. Or if you don't yet have it, do a git clone to get a fresh new copy. I have a whole slide on how to do that for you if you don't know. In about 5 to 10 minutes, we're going to start with Decker French today. And then at the halfway point of the first hour, we're going to switch to Ryan Morsony. So we have two delegate presenters today talking about nuclear transients and then force photometry with DP0.2. As always, the second hour will be breakouts. This will be driven by whatever kind of breakout sessions you want to see today, whatever you want to work on. And as always, the main room will be open for a general Q&A, any issues you might be having, questions, that kind of thing. But we will set up those breakout rooms and choose topics at the halfway point, as usual. So today, if you don't already have a copy of that Delegate Contributions DP0.2 repo, these are the instructions for how to get one. So once you're in the notebook aspect at data.lsst.cloud, you open a terminal. Then you also have to point your browser at GitHub to the right repository. The link is here. The link is also in the chat. You need to click that code button, the green button that you will see here, and you need to copy what shows up in the little pop-up window. And then back in the notebook aspects terminal command line, you do this git clone and then paste what you got from the GitHub website, and it will get you a whole fresh copy of the repository that contains the notebooks that we're going to be using today. I'm going to put into the chat again the link to today's slides that have these instructions, and also the link to today's repo in case you're just joining us, so that you have both of those links there. Once you have a fresh copy of this repo, you'll have a new directory called Delegate Contributions DP0.2 in your home directory of your notebook aspect. And then the notebooks that our speakers are going to be using are in there, and they will instruct you which notebooks exactly to open so that you can work with them. I can see more people still joining. And since you won't see the chat history, just one last time, link to today's slides and a link to today's repo. All right, coming up in the future, next week at this time, we'll have Stat Club as usual. The next delegate assembly is actually going to be Friday, November 18th, because we start running into some holidays. And so we'll be off 1 week, so there'll be no assembly, then a Stat Club. Then we'll have delegate presenter Vincenzo Petrecca is going to be talking about analysis of DIA sources. So that should be another great delegate-led assembly on November 18th. And a reminder that Friday, December 9th will be the last delegate assembly of the year. It's going to be sort of a DP0.2 year in review. We'll go over everything that was new this year in case you missed it. And then we'll do some delegate-led flash talks. There will be more information circulated about that in the future. Another announcement is that as of yesterday, new versions of some of the tutorial notebooks were pushed to the prod branch, which means they should be appearing in your tutorial notebooks directory in the notebook aspect of the science platform. The updates were to notebook 03A and 07A, both got some updates, minor ones in 03A, but 07A, which is a time domain notebook, now has a new section 4 that's showing you how to use the new force source on DIA object table. So it's got a bunch of information there. So if you're a time domain astronomer, check out the new version of 07A. Then there's two new notebooks, 09A and 09B, which show how to create a custom COAD. So if you don't want a super deep COAD, maybe you just want a COAD that's made out of visits from just 1 month that just had a certain, were at a certain air mass, or only had like the very, very best seeing, whatever, any kind of custom COAD you want. Notebook 9A shows you how to make them. Notebook 9B shows you how to run source detection on your new user-generated custom COADs. So that's what's new in that directory. If you have any issues with your tutorial notebooks not automatically updating, please do ask for help during the general Q&A in our second hour, or submit a GitHub issue or post to the forum. Just let us know in any way if we can help you with that directory. So I'm going to just pop back to here. And if you have any trouble getting this delegate contributions DP0.2 repository local to your account in the Rubin Science platform, pipe up now. Now is the few minutes where we can help you. Either in the chat or just unmute. Any questions or comments about those announcements? If there's no issues with getting the repo. Still just going to give you a minute to actually try. Okay, sounds like no issues with getting a new and updated version of the delegate contributions DP0 directory. That's great. In that case, we are, and if there no other questions came up either, so I'm going to stop sharing my screen. I'm going to turn it over to Decker.
All right, thanks. So let me share my screen. Okay, so for this notebook, I set this up in a medium container. So if you've got medium or large, I think that should be fine. But yeah, so hopefully everyone's had a chance to navigate to this notebook from the Delegate contributions folder. So the reason that I made this notebook was I wanted to play around with this general idea of using the catalogs and trying to match up transients or some variable source with the host galaxies that is in.
Sorry, Decker. Oh, never mind. I see there's only one actual notebook in your nuclear directory.
Yeah, so there's the one notebook, and then actually the other file there is a HTML readout of what happens if you run all the cells in the notebook. So if for some reason it's not working, or you just want to quickly see what all the output is, that HTML file has the output. And the reason I made this HTML file, I'll show you as I get to it, but one of the queries is truncated for time and ease of kind of doing this live and debugging. If I set this to run for 2 hours or something to do a long query, this HTML shows the result of that. So if you're curious what it would look like to run super long query, this file has what that look like. Yeah, so in this, let me see, I'm going to make myself a copy of it. And this may be the right one. All right, a fresh copy. So in the transients that I'm interested in for my science are things like AGN flares or a tidal disruption event for a star around a supermassive black hole. And none of these are in the data preview, right? And so I wanted to still use the simulated data for my science. And so the way I decided to do that was to say, well, in looking for real black hole transients and real variability, we're going to have to know what it looks like when there's nothing there, and more quantitatively to characterize the noise that's underlying the nuclear variability. Since we know about the noise underlying supernova or things far away from a galaxy, but if you have say in a galaxy a bright point source in the center, right, you have the core of the galaxy, what does that do to the noise? I expected that we should get a little bit of extra noise because in the difference imaging we have this bright galaxy. So I wanted to quantify that and use this as sort of a test for playing with the data. So I'm going to start here. So this is sort of what I put in text here, but there's 3 tables that I'll use. And the schema for each ones are on this site, on the DP0 site. But essentially, object is where I'm going to get the information about the galaxies. So these are the properties from the deep coads. And I'm going to use this for identifying which objects are galaxies and also getting their colors. Then we have dia object and dia source, which are the new things for DP0.2, where dia object is going to have those sort of parameterized set of quantities for the light curves. So not the individual fluxes with time, but things like the standard deviation of the flux in a band, things like that. And then dia source, this is the properties of those transients in each of the single uplink images. So this is where we'll ultimately get the light curves. So to start, I import a bunch of packages, set up my cosmology, things like that, based on having adapted this from some previous notebooks. And then I set up the tap service. So hopefully this is familiar from a previous notebook. I'm not sure I can do justice to a good explanation of what is going on under the hood there, but I would point to some previous notebooks for that. All right, so with our packages and our tap service, the next thing you want to do is identify transient sources that are in the nuclei of galaxies. So first I need galaxies. And so the main parameter of interest for this is in the object catalog. I want this parameter ref extendedness to be equal to 1. So this is galaxies that are extended, so as opposed to a point source, in the reference band, which is typically the I band for this case. I checked, do we get something very different if we use require it to be 1 band? It wasn't that different. And then, so this is what that query looks like. So I set the max records to be 1000, and this took about 15 seconds, so this should be pretty quick. But let me start this and then walk through it. So the query is to select some coordinates, the object ID. I want to use detect is primary because I'm going to set that equal to 1. I'm going to say only give me the objects where it's a primary section to get the deep blended objects only. And then I'm going to require ref extendedness to be equal to 1. And I'm also going to get these, take the fluxes in U and R and turn them into magnitudes for my table, because I will find that easier to work with. And one final constraint, I'm going to require that the R band magnitude is less than 18. So I want to do something with the host galaxy properties, but without like photoses or something. I worry about the K corrections for things that are far away. So to get around all of that, I'm just going to try to find nuclear transients in the bright galaxies as sort of a crude proxy for the nearby galaxies. All right, so that's run. That's actually a little bit faster than it was when I wrote this, so that's great. And we can look at the results to make sure that makes sense. So this is what we're getting, this table that has magnitudes, all the FX and this is 1, and that all looks good. And there's 1,000 things in there. All right, so having found the galaxies, the next step is to identify nuclear transients in these galaxies. And I put transients in quotes because I really just want anything that has been, that's been put in this Dia object catalog. And so I'm going to use the coordinates from this galaxy search to cross-match. And the reason that I can do this, I can just say, do a simple, RA and DEC of the galaxies, as close to the RA and DEC of the transients and get away with that is because these are nuclear transients that I'm interested in. In general, this sort of thing is more complicated, right? For something like a supernova that's farther away. And so I object to some recent work that tries to do this transient host matching more generally for something like that. But for the nuclear transients, it's easy to find what the host is. And so what I'm going to do is say, find me any transients that's within half an arcsecond from the galaxy coordinates. These are likely associated with the nucleus of the galaxy. And so a few more constraints that I'm going to put on this. There could be multiple Dia objects per galaxy. For this, because I'm just looking at the underlying noise, I'm only going to select one of them, but sometimes there are multiple. And I haven't quite looked into why that is. If those are like half an arcsecond at either side of the nucleus or something like that. For this purpose, I just want any of them. And because I want to look at light curves, I'm going to require that these sources have at least 20 G-band data points. Less than that, and it's hard to really study or look at the variability. So we're going to require that there's enough data. And so this is what this looks like. So this takes about 3 minutes to run. And this is where if you want to see the longer query, you can look at the HTML file. So because we selected 1,000 as our maximum of records for the galaxies, I'm going to have to do this for loop over that number of galaxies. So I'm going to have to find the nearby Dia objects for each of those 1,000. If I didn't do that, so this is now that larger notebook, just as HTML. If I increased the number of max records to, in this case, 10,000, right, then I could loop over all 10,000 of those, and that took longer. You can see in this case, that took 30 minutes, and we could have it go even longer than that. In this case, this will take about 3 minutes. Let me set that running while I talk over the rest of it. So I set up my table to collect my results in, and then I iterate over each galaxy. And I say, all right, here are the coordinates that I want. Here's the radius I want to search in. And the meat of this query is this command where I am saying where this circle that's between my coordinates and this radius contains the point of the RA and DEC of anything in Dia object, get me this collection of things, and require that I have more than 20 data points. That's sort of what's going on here. And so it does that, and then if there's nothing in that, it just continues, and then it puts 0 in my matches column here. If it's not 0, then it populates all of these. So what I'm collecting is the Dia object ID, which I'm going to need to get the light curve data, the number of matches, so I can see if it's more than 0, and then this G-band total magnitude mean and standard dev, as well as the PSF flux mean. And so I'll note that here I'm using the total flux measurements instead of, say, the force source measurements, which will make a slight difference. And I've also pulled the PSF flux to test some of these differences. So then there's a number of different ways to select the total flux that one can play around with. All right, so that is running. And so let me pause to see if there's questions. Yeah.
Decker, the in your query with the circle, it gives the center coordinates and the radius, and then it says =1. What's the =1 about?
So that is for this. So this is a statement of does that circle contain the point? And if it's 1, that means yes. And if it's 0, that means no.
Thank you.
Yeah. Thanks. Other questions? All right, so should have ran that earlier. So while that's running, I can actually go over to my output and look at the rest of that. So on my longer query, this is what this looked like. So if I do, this results table and look at it, this is the data. So in this case, there are 10,000 rows because I had 10,000 galaxies, but not all of them have a match. If we look at this matches column, you can see that a bunch of them are 0. There's not anything. And so none of these fluxes were populated. And in this case, about half of them had a match and half of them didn't. And that by itself should tell us that actually if we had any doubts of whether these were real or spurious transients, that, we should not expect that half of all galaxies in this, thing had a real transient. And because there's some randomness in actually what you get served in the query, when I was testing this, anywhere from like 1/3 to 2/3 of the galaxies had a match.
Quick question: what happens when your match is equal to 2, which is one case at least?
Yeah, so if matches is equal to 2, I only pick the first one to put in this. And so because I'm just interested in like what's the typical variability, I'm assuming that there's nothing different about the cases where there's 2 matches versus 1 match. That might not be the case, right? So probably the next step is to say that if there are 2 matches, to either combine the light curves, assume they're from the same source, or to add extra rows to the table if there's 2 matches to look at all of them.
Thanks.
Yeah. All right, so that has run now on my short version. And so I can inspect these results, which are quite similar, and see in this case, how does that compare to my half before? A little bit less than that, right? I've got 434 out of 1,000. All right, so the next thing I want to do is take some of these matches and plot them, look at the light curves just visually. So I need to do another set of queries to do this, because in Dia object, I just have that metadata and I don't have the light curves. So what I need to do is to take that Dia object ID and use that to query Dia source. So this is another case where I'm going to have a set of queries in a for loop, but I'm only going to look at the first 5. So this should be pretty quick. So I'm going to only select the cases where there's a match. So I'm going to make this new table called matched, which is just that results table where matches is more than 0. I shamelessly stole all the plotting commands from the Supernova notebook, also to make it consistent if you've been looking at that or playing with that. So for just for those first 5, I'm going to do this query in Dia source. So I'm going to select the coordinates again, the Dia object ID and the Dia source ID, the filter name, the time, and the total flux converted to magnitudes again. And then where the Dia object ID is equal to the one that I'm getting from that match. And so I iterate over that and I plot the data. So this is what those look like. Where, let me just scroll so you can see it all. This is my legend for those colors, same as before. And you can see that most of them look, pretty flat. Like it doesn't look like these are real transients for now. And the reason that that you might have expected that there'd still be anything in here, even though there's no AGN or tidal disruptive events in the data, is because there could have been like a supernova. So one of the things that I haven't yet done but want to is to use the truth tables to find where the type 1As are and to focus on those and see how do those look when they're close to the nucleus. But it doesn't look like at least for these 5, any of them are like that. If your random draw has gotten you something different, I am totally curious about that. But for these, they look quite flat. All right, so the next few cells I have are to look at more of the metadata for the dia object information to see more about these sources. So for example, we can use the dia object information to look at the mean flux and just plot a histogram of that. And it looks reasonably symmetric around 0 in that the actual flux that we're getting is consistent with this just being noise, where sometimes that scatters a little bit up or a little bit down, but that the PSF flux in the difference image is mostly consistent with 0. Some of them have negative mean fluxes, and I don't know if that's caused by noise or if there is a real transient contaminating the reference image. It could be either. And then again, we can look at, we can zoom in and look at the mean and median. And, sometimes they're, both barely positive. You can see in this case, the median is slightly negative, but it will depend on the actual data. All right, so I wanted to find things that were interesting, things that had, something that might look like a transient. So, doing this quantitatively, and robustly defined transients is its own own set of things to consider. But to do the crudest cut, I just wanted to look at the cases where this G-tope mag sigma, so just a standard dev on the magnitude, where that was the highest, because I figure those are the cases that, if there is a transient, that might show up there. And so you can see that, they're mostly small, but I was interested in this kind of tail end here, the cases where G-tope mag sigma was high, to see what's going on with those, if those are the most variable. So I selected just these that were more than 0.2 mag and looked at the light curves. This has usually worked, though Baba sent me an email a bit ago saying that sometimes you get less than 5 here. So if this doesn't work, it might be because you had less than 5 objects that are more than 0.2 here. So if that is the case, then just compress the number for these. I still need to put that in the actual notebook to account for that. So this is the same code as before. It's just going to plot these results. And so these fall into kind of 2 camps, usually something like this, where you can see that it's really just the one kind of anomalous detection for this that's causing the high standard dev, which is, an example for why you should probably do something more robust than just a sigma for selecting real transients. There's also cases like these where, this does look like, something that we might mistake for real AGN variability, where, this is just noise. There's no, damp random walk being put in here, but, by eye, this doesn't look that different than an AGN light curve. So this is a sort of behavior that I was interested in to say, this sort of thing can, potentially limit what we're pulling out of those searches. All right, so as a test, getting back to the host galaxy cross match, my thought was, well, if we think about the types of galaxies that have a lot of light in the core versus not, I should expect that the red galaxies have these high statistical indices or a cuspy versus, our bluer galaxies will be more, the classic disk. And so I was curious, would the red galaxies have higher, a higher rate of noise in the nucleus than the diskier galaxies? And so, the right way to do this is to actually measure some structural properties of all the galaxies. But as a first test, we can use the colors. And this is why I did the magnitude cut, because when I just plot the color for the galaxies, just U minus R, I recover like a classic galaxy bimodality where, we've got blue ones, we've got red ones. And had I not done the magnitude cut, we would worry about having to do the K corrections to get this. And so that was all the galaxies. I actually saw something slightly different when I looked at just the ones that had a match in Diosource, where actually it was more the blue galaxies than the red galaxies that had a match at all. So I don't know what all causes that. I think it's either an effect in, some of these in the blue galaxies are probably real supernova type 1As, but maybe it's also a systematic effect. So even though I don't have this clear bimodality anymore, I can still look at, dividing the host galaxies into red and blue. So I did that based on a U minus R color of 2, where, if you're over here, you're a red galaxy, and if you're over here, you're a blue galaxy. And so I took the average value of this G to max sigma for blue versus red and looked at this. So if this is the blue and the red galaxies, this y-axis now, what's the average standard dev of that total G-band magnitude as a crude proxy for, how much noise are we getting in these light curves that should be mostly just noise and not real transients. And this depends actually quite a bit on how many galaxies I have. And I think it's because these arrays are quite large, maybe with some large outliers. So this is the reason that I put the full thing in the HTML file. So I get somewhat smaller errors if I, up the number of galaxies in it, where I have, maybe a factor of 1.5 more noise in the red galaxies than blue galaxies. Depending on the sample I pick, that doesn't always appear to be the case, right? You can see it's similar here, but actually this y-axis is a little bit different. And I bet for many people, this is actually reversed. I tried this multiple times, and with only a sample of 1,000 galaxies, there is a bit of scatter. All right, so I think I went through that a little bit fast, but I think there's a few minutes for more questions. Yeah, Douglas.
Oh yeah, it's a very, very nice notebook. I like it. One question for helping determine if there were AGN in the DC2 in the DP2 data set. What is the typical variability in say magnitudes for a real AGN? Is it like on the order of a magnitude or so? And would that be a good cut to make on a real sample, or
So
smaller? Is the variability smaller, or?
So I think, so the AGN variability isn't in this sample, but I think it is in one of the dust simulations that was in it. And so what the variability is depends on the time baseline that you consider with like this standard structure function, where on like sort of weeks or months, it's something like, maybe 0.1 mag, and then getting into years, you're getting into, a magnitude of slower variation on those timescales of many years.
Okay, thanks. Good to know. Thank you.
Melissa, yeah.
Yeah, I just wanted to make a couple points about some things that are different about DP0 than the future that are going to change the interpretation a bit, and just some things about LSST in general, right? Because we start by limiting and only selecting the very brightest galaxies, and galaxies brighter than 18, that's quite bright. for LSST. And so even in some of the first plots, I think it's the first one in section 2.3, it's the total magnitude that's being plotted over time. And you can see some of them are like right up at the saturation limit. So there's going to be issues right away in the difference images. So you might very well find a lot of like spurious sources in the difference image. So I would guess that's where that, you're kind of matching half of all of these super bright galaxies to some kind of nuclear transient. So right away, that's probably where that's coming from. And for DP0.2, there's been like detections done in the difference image, but then there's no sort of real bogus, there's no spurious classification happening. And in real life in the future, that would happen. And so I would hope this issue always remains of like bright stuff. It gets messy in the core. But I think in the future, there'll be a lot more resources for people to sort of start weeding those out. So I did want to make that point here that this is a sample that is the most prone to spurious sources, and there's currently no like protection for people against that. So yeah, I see Nevin raised his hand. Maybe he wants to comment on that too.
Well, yeah, it might be exactly what you were describing. I wonder at these AGNs, these sources that look like AGNs and they're obviously not AGNs, what happened there? Because the errors are probably much smaller than the spread in the data. Yeah. But you probably don't know that, right?
Yeah, I don't know. I mean, this sort of thing is definitely just there was one, that's
right.
It's like one faint one. But for these, I should see are these the ones that have something else in common. Are there flags, even if it's not like a real bogus thing? Are there flags if some sort of severe noise was added, or?
There are some flags, but also there's going to be a problem also because it's when you're getting like the total flux value, it's a PSF that's just put down right at the location of the DI object in the direct image. So if you have seeing variations, like you're in the middle of a bright galaxy and you've got seeing variations, it's going to be pushing more or less luminosity in and out of your PSF region. So you're going to, with that particular data product of using the tote flux at the location, that's basically it's a force source at the location of a GI object, you're going to see like variability just from image to image like that.
It's kind of amazing that the simulations can make such a believable, spurious variability.
Yeah, what I haven't done yet is to, try different ways of getting the flux to do the force spectrometry, because for real AGN, right, we'd want to, look over the whole galaxy to get around the seeing thing. And if that's, doing something like that makes it go away, then that's, super reassuring for not getting this kind of big AGN-like behavior.
Yeah, so overall, I think this is still a really great demo, and it's a really good way to start digging into all the different data products and to start like building your notebooks for nuclear transient. So we do have to switch to Brian now, but I wanted to thank Decker very much for the presentation. And Decker, do we have you for the second hour?
Unfortunately, I have to go for the second hour because I have to get ready to teach my class. But I'm on like the Slack and stuff. So please like send me questions, or if you've got trouble with the notebooks or anything, happy to chat more.
Super. Yeah. So contact via direct message in the forum to Decker French is probably, easy. Okay. Awesome. Thank you so much for being here and for doing this today. That was great. Let's switch to Brian. I see your video's on.
Hi.
Ready?
Yeah, let me share my screen here. If I can, there we go. Okay. Make that as big as I can. So hi everybody, how's it going? Let's see, so I'm Brian Morsony. I'm a professor at California State University Stanislaus. I guess I should start by saying Cal State's hiring this year, Stan State. Our ad will be out soon. We're hiring 2 tenure track positions in the physics program and want at least one of them to be in astronomy. So if any of you or your postdocs or your students are looking for jobs, keep us in mind. Let's see, you should be able to find my notebook here. If you go to the like delegate contributions, then it's forced photometry at location, I think, and there's just one notebook in there that should come up. So the idea here was, you've got a transient, you've got a supernova or whatever it is, and so when that source is detected, when it's bright enough to actually, trigger some threshold, then you get photometry of it. But I wanted to say, well, what does it look like at all the other times when it's not that bright? I want to know, when was the last time it was detected, or what's the upper limit, or whatever. And I started doing this because when the DP0.2 data came out, originally it had the photometry for the detections, but not like the non-detections. I think now there's forced photometry there as well. But thinking about when we have real data coming in, this could be, okay, you've got a new transient somewhere, you want to go back and get the prior light curve, or you've just got transients from some other survey. I do gamma ray bursts. So, you've got some Swift GRB, you want to see, is there anything there in the Rubin data, or I don't know, radio transients with something, and you want to see, is there an optical counterpart? So I had to figure out how to kind of do this, take a visit and do photometry at some set of coordinates. And how I managed to do that was using this fake source injection notebook that Jeff Carlin had written for DP0.1, and kind of repurposing it to do, basically to add fake sources and do photometry, but do photometry on the images where we didn't add the fake sources. And I have no idea if this is the right way to do it, but it seems to be working okay. So let's see. So if you want to follow along, so there's some introduction, and then I load a whole bunch of packages and parts of the LSST pipeline. And it should say those are all loaded. Then I've set this up where I define a bunch of functions, and then after I define them all, we'll have examples of actually running them. So this first couple here are make fake star and add fake stars. These are taken from that, add fake sources notebook that Jeff had written. So these are functions that will load up an image, or you've given it an image, it loads, you've given it a reference, a visit, it loads up that image, and then it goes through and you give it a list of RA and DEC and magnitudes, and it will add a star of that magnitude at that location, or it can be more than one. So it goes through, it's gonna get your image, from this thing that it's loaded here. So what I do is this from the butler, it gets the image, then I make a copy of it, which is going to be the one I add my fake star to. Goes through, gets some information about it, tells you what the noise is and stuff. Figures out what the location in, or gets what the coordinates of this image are. Then it's going to loop over these sources. Usually I just give it one, but you can give it whatever you want. It's going to figure out where that location is in this actual image. If the location is either not in the image, if it's off the edge, or if it's too close to the edge where like the PSF wouldn't actually fit in the image, then it doesn't add the source. It just says, okay, I'm going to skip this one. But if it's okay, then it will add the source in. So it says, okay, my image, some part of it, I'm going to add this thing that I created. which was this make fake star. Whoops. Hopefully my computer doesn't die as I'm doing this. Is this make fake star command, which had you have a position, an intensity, and a PSF. And you can feed that intensity as whatever magnitude you like. Okay, so that's just kind of some utility functions. Let's make sure they're loaded, and it should say ready. Our next function here is the one that's actually going to process these images. And so I have this, going back to the one before this, what is this? Add fake stars returns the original image, which is this calxinp, and then I have it return the one where I added my fake source. So that's the with fakes one. So to process my fake images, I give it two images. I give it my original one, and then I give it the one where I added my fake stars, which is I call new in this function. And I set stuff up, I'm going to return a data table and that sort of stuff. But then I go through and I set up, some of this like initialize, characterize image, and initialize source detection and things. But then what we're going to do is we're going to basically reprocess this image. We're going to go through and redetect sources and redo the photometry on those sources. And again, this is kind of borrowing from this notebook Jeff Carlin had written. And there seem to be a number of tasks that are in there. The first is this image characterization task, and I honestly don't know what this is doing, but it seems to take a long time to run. It didn't really seem to change anything, so I just commented that one out. Maybe that's a bad idea, but it doesn't really seem to change stuff.
I think you're okay because calexps have already been characterized.
Yeah, I think maybe
So
because it's already been done, it's okay. If I was doing like raw data or something, maybe it wouldn't. Yeah. Okay, so it already kind of knows what the PSF of these images are and everything. So it gets the PSF, that kind of stuff, tells me what it is for that image. Usually should be around an arc second. So then what I do is I run this source detection task on the new image. So that's the one where I added the fake sources, and that'll identify, every source. And I think it's, above a signal to noise of 10 or something. And then I get that back. Then that's giving me kind of what the footprints of all those sources are. Then what I do is take that and then do deblending, but on the original image, not the one where I added the fake stuff. And then do this source measurement task with the catalog of sources from this deblended thing, but on my original image. So it thinks there's a source at the location I've added something fake, but there's not really anything there. There's just whatever was in the original image. But it'll tell me what the flux is at that location. And this does it for all the sources in the image. So, a typical image, you have maybe, a few hundred to maybe, 1,800 sources, something like that. It's doing the photometry on all of them, which takes a little while. So it takes a few seconds to do that. And then, it's going to copy it and put it in a table. And I think I convert the fluxes to magnitudes as well. So they're in my table. And we'll see, what that looks like. So that's the kind of what's actually doing this photometry is this function, and really this source measurement task. Then my last function here is kind of just a wrapper to get this all to work. So I have all my setup and everything to feed in, make my images with the fake sources, do the measurement on them, and give me back data. And it will go through all the visits that have that source in it, or I can, have a start and end index if I want to do just a subsample. And so it gets fed a location and a band. So I want to do like all the U band or all the R band or whatever. So let's see. So then we go through, we do our normal setup for DP0.2, set up a butler so it's ready to go. In order to find the visits that have my location, it makes a little triangle, which again, I'm copying from what Jeff had done. I think, you have this HTML pixelization, which a higher level means you make a smaller object. It makes some triangle down here. And then we do a query where it says, if that triangle overlaps this exposure and the band is what I want, then put that in my list. So I get this list, my database refs, and I put it as U because I started doing everything in all the bands and then cut that out. So that's has all the visits for whatever band I picked. And it tells me how many there are. And then I do, I sort it. I don't know how it's sorting it. It doesn't seem to be by visit number or by date or anything, but at least it always puts it in the same order. If I don't do that, then this database query is giving you things in just kind of a random order to begin with. But that was good enough. I just want them all in the same order each time. And then out of that, I take just the ones between my start and end index. So, if I just want the first one, I can put 0 and 1 for my start and end, and it just picks the first one. Then I set up my fake star to add my fake source. So make an array that's just the RA and dec that I gave it. And I make it a 20-second magnitude source. That's, fairly faint, but bright enough that it's detected. So it'll be there. You can make it a brighter source if you wanted, but then basically you're getting a bigger footprint that you're going to do photometry on. So I figured, should keep it relatively small, or at least I think that's what would happen. But I haven't played with it too much. This seems to work fine. And I should say, if there's an existing source there, that's also not adding very much. So, it would make the footprint maybe a little bit bigger, but, if there's a 20th magnitude source and you're adding a 22nd magnitude on top of it, it's not a very big change. So if there's a real source there, it won't change things too much. And then I'm going to loop through, and for each of these visits that it said my source was in, I'm going to add my fake source and get my 2 images back. I'm going to pass those images to my process fakes procedure, do photometry on them. And then that'll give me back a table of all the sources that it detected and the photometry on all of them. But I have to go through and find, well, which of those is the source that I want. So it goes through and gets the coordinates on the sky and will select out, well, if I want it to, it'll plot an image of all those sources, and then it plots a box where the source that I wanted should be. And then it goes through and it looks at the separation, and it says if there's a source within 1 arc second, then that's my source that I want. And I think if there's more than one, it just takes the first one, and then copies all that data into a table, and then just returns, makes a table of just that one source for each visit that I went through. And if there is no source within an arc second, so like if my source was off the edge of the detector, then it just gives everything minus 99.9. So it gives the magnitude and the magnitude error and the flux error are all just minus 99.9. So I know that was a bad visit. And then it'll, put out a table. And it prints out actually for each visit what data it's putting in the table, just in case you're following along as you watch it work. So those are what my procedures are going to do. It's going to say, okay, I want however many visits at this location, give me the force photometry, loops over them, makes fake sources, then does photometry on the image without the fake source, and then identifies, okay, which source is at the location that I wanted. Let's make sure that's all loaded up. Okay. And then I have some examples where I've taken a look at this. So the first one here, so I give it some random seed just to make sure everything's reproducible. I picked a location where I happen to know there is a supernova in the data set. There's, a type 1A, and it has some object ID if you want to look up which one it was. I picked the U-band as an example, just because it runs a little bit faster and there's a few less visits in the U-band. And for this first one, so I'm going to give it this photometry at coordinate all visits with my right ascension, declination, band. I'm just going to pick the first one. So start index 0 and index 1, and I'm going to have it make this, this image of all the sources that it finds. And this should take a few seconds to run, hopefully. I may not run all of them just for time. So it goes through and says, okay, we found 52 visits at that location. It's just going to do the first one. It found 428 sources that it's measuring. And in this case, my box is actually off the edge of my detector. So for this first one, the it said this little triangle I made overlaps this visit, but the source is actually off the edge, so it doesn't measure anything, or it's too close to the edge. So it just puts all this, minus 999 data in the table. The closest source was 40 arc seconds away, so that's a bad source. Okay, so let's pick a different one. The second one in this list I know, is at least in the detector, so same thing. We can run it. Should go through and do the same thing. So the size of the triangle is about 17 arc seconds, is what this first line is telling me. Okay, and this time it loaded it up. Here's all the sources it detected, and my fake source should be somewhere in that box, and there's a source there. So that's the one that I added. And there's no real source here. So it measured the flux as, God, this is in nanojanskis, I think, right? So minus 34 nanojanskis with an error of 95, which for U-band sounds about right. So there's really nothing there. And then, of course, for the magnitude, it got not a number because you try to convert a negative number to a log. It doesn't like that. And we can print out what this little table that it returns looks like. So here it was just one visit. It gives us the location, the date, the flux error. What else do we have? Magnitude, magnitude error, and the separation. And so this source was only 0.05 arc seconds away from the location I wanted. That sounds good. So it's a good match. Let's see. So now let's take a look at an example where we're going to load several. Here I'm just going to take 10 for time. This takes about a minute and a half to run. If I did it for all 52 visits, it takes about 7 minutes or so. And just for time, I think I'm not going to actually run this. So it's going to go through 10 sources, starting with whatever the 25th after I sorted it was. And I have it not print the images out this time. But I'm going to get my table at the end here. So we see there were a number where the source was too close to the edge or off the detector, or in the gap between chips or whatever. There's a number where it did photometry and, as we should expect, there's not a real source. But then there's a couple where there actually was a detection. So like this one, the third one down, the flux is, 450 something nanojanskis and the error is about 100. So, okay, that's, a 4 sigma roughly detection. And then I made a little piece of code here to sort of separate out these 3 different types, because we should have, bad sources where we didn't get any measurement. We should have upper limits where we didn't detect anything, but we can say, what's the 3 sigma upper limit? And we should get real detections where we did see a source. So I made a little bit of code to go separate those out. So I take the time of each visit, the flux and the flux error. First, I just make an array that's going to be true if it's a good source and false if it's a bad source. And since the flux error should always be positive, if it's less than 0, that means it was off, it's minus 99.9, it's off the edge of the detector. So I say if it's less than 0, then it's false, and otherwise it's true. Then I make another array which tells me if it's an upper limit. So this upper limit array will be true if it's an upper limit and false if it's not, if it's a real detection. And I'm also going to make a corrected flux. So if it is an upper limit, I'm going to make my flux 3 times whatever the error is. And I'm going to say it's a real source if it's, if it's more than 3 times the error. So hopefully that's a 3 sigma upper limit. Maybe, you should make something more strict, but a decent start. So go through and say, if the flux is more than 3 times the error, then it's not an upper limit, and then use the original flux, not this corrected thing. And so then that's going to give me, I can go through and have an index array for my 3 different types of sources. So my bad sources, my upper limits, and my detected. If it's not a good source, then it's bad. If it is a good source and it's an upper limit, it's an upper limit. If it is a good source and it was not an upper limit, then it's a real detection. And then I slice up my time, my flux, and my flux error into these 3 different arrays. And then I'm going to plot them. So I'm going to plot my detected sources with error bars. I'm going to plot my upper limits with arrows, and I can plot the bad visits, and I'm just going to put them all at 0 because we didn't measure anything. And for these 10 sources or these 10 visits, I got 4 bad sources, I got 4 upper limits, and I got 2 actual detections. And so it looks something like this. And, so this is the date versus the flux. So great. So you can kind of see it. Here, this may not be in the notebook you're looking at, and probably don't run this because it takes about half an hour. I went through and did the whole R-band light curve. It takes a little longer because there's more visits. There's like 130. And also there's more sources per image, which means it takes longer to do the photometry. And I have to scroll all the way to the bottom because it puts out a bunch of output that I don't really care about. And then I'm going to do the same thing, divide it up into, detections, upper limits, and bad sources. And here's what my light curve looks like. So I get 30 bad sources, and here I put it on a log scale because it was, brighter in the R band. I get 96 upper limits, and I get 6 detections. 5 of these seem to be real detections, that's the actual supernova. And then we even get one here that the flux it measures is more than 3 times the error bar. But I think that's probably not a real detection. That's just some, we got some noise or something that put it over that threshold. So it is, I printed out the flux and the limits and everything. Let's see, I think it is this one. So it's, the flux was 1200, the error was 300. So, okay, it says that's a source, but just barely. But it's, like, I don't know, what is that? 80 days before the supernova happened or something. So I assume that's not real. That's just some, it got above the noise threshold. So that's what this would look like. Sometimes you're probably going to have actual detections at all of these times, because this could be, in a galaxy and there is some actual flux at that location. And when you measure it, it gives you something. But, hopefully that would be fairly consistent. And then you see where the transient pops up. If you don't have, a transient there, you might get nothing. Yeah, so that's kind of what I came up with. This is pretty slow because it's doing the photometry on all the sources in that image that you pick out. There should be a way to make it faster by just doing it on the source you want, or near the source you want or something. I just haven't figured out how to make that actually happen yet. I don't know if I can do like, just take a sub image that's small or something like that and just do it there. That might be possible, but yeah, I just haven't had time to figure out how to do that. So if you want to do this, a full light curve and all the bands, it's going to take a couple hours to run. But that's okay. That's not too terrible. And yeah, questions. Yeah, Melissa.
Yeah, two questions. One is that I missed or forgot or lost where the fake sources are being used.
Yeah, so the fake sources being used, so I'm taking my image, I put in a fake source, and then it detects where there's sources in that image. But then I take it back out again. I give it the original image when it does the photometry. So it's using it basically to add a source to the list of detected sources. I add a fake source to the image.
Oh, I see. So you're not like putting in fake sources, because you get an upper limit out of this. And one way to do that is to put in fake sources at a range of magnitudes and then see what's detected. So I thought maybe that's what you were doing, but you're just
No,
okay.
Yeah, for this, I just said, if I get an error on that sort, like even if I don't detect anything, I still get an error. I get a flux error. I said if it's 3 times the flux error, it's a source. If less, it's not. Yeah, there's probably better ways to do that and get, a better threshold, but I haven't tried that.
I think you're doing it the right way. So you mentioned when you do source detection, it does it on the whole calyx, but I'm not sure how to tell it to only do detection on one spot.
Right.
Measurement step, you do give it the coordinates. And so there you could just give it one coordinate, and then you're doing force photometry, which is basic.
Right. Yeah. So that'd be the other way, would be do the detection on the whole image, and then identify this is the one I want to do photometry on based on the coordinates. But I don't know enough about what that data structure looks like to actually pick out that one. But yeah, it should be possible.
I just wonder, I think you don't have to redo source detection on the whole image. There's a step that's just measurement, and you give it sources. And so if you just take out all the other sources from that, or you just only give it only the location, it'll just do measurement there.
Yeah. So I'm sure there's some way to do it. I just haven't been able to dig deep enough into what these steps are actually doing to find it.
Yeah, it is easier if you're just using the science pipelines to just sort of
Right.
do it the default way and then pick out what you want.
Yeah. So I'm kind of doing, all the sources, then pick out what I want at the end. But there must be a way to pick out what I want at the beginning or in the middle somewhere, and not have to do everything. And this add fake sources is kind of a useful function I found. So, if you want to add, your own transient or whatever and reanalyze the light curves, you could do that with this as well. Just don't take the source back out. Yeah. See, any other questions about this one? If not, I can stop sharing my screen, I guess, and I'll be here a little bit longer. I have to go probably about 10:30 or so, but I'll be here a little while. Thanks.
Okay, yeah, thanks, Brian. Yeah, I just got distracted. I was looking again at your code.
Yeah. No problem. Yes,
Yeah.
any suggestions are more than welcome. So
Yeah, I think it's like I think, and maybe this is something I have to look into. I think it's this step where you're doing source measurements that you gave it all of the sources that you had detected.
Right.
But I think you could manipulate this to be only like the location of interest.
Yeah. I think I can take just the source I want out of that catalog. It's just I have to figure out which source in that catalog is the one I want. And I haven't been sure how to do that or how to pick out one and, make my own catalog. So it's, it was working at least, but that would be, making it faster is always the next step, right?
Yeah, it's working. Yeah, and I haven't done that either. And
No,
make my own version of this sources that just is the location.
Right.
Right.
So I know it's possible. It's just getting it to actually do it.
Yeah. Okay. Let's pop back to here. So this is the breakouts portion of our delegate assembly. And this is where, let me just reopen my chat. Anyone can suggest a breakout topic. If you want to co-work together on any of the notebooks that you saw today, you just want to take a deeper dive into what you just learned. Rooms for that are good. General Q&A is always good in the main room. So just gonna let you think about it and suggest what you might want to work on.
Douglas, I'm going to work on the criteria that you showed me from that 2009 paper on how to use colors for Sloan Digital Sky Survey to determine the type of star. So I'm gonna try to plug those in. I don't know if we need a breakout room for that. I'm just gonna.
We can do that. I hadn't quite decided what I was going to do. I definitely have a backlog, but one of the possibilities was to see about how to implement the that code that does calculates the synthetic magnitudes in the LSST data that you might want to use later on when you're doing more the later on bits to maybe not just the black body law, but to star spectrophotometry.
Okay, I think so. I think I'll stay in the main room and work on this stuff, and then we can talk a bunch next Friday.
Okay, it
Good.
sounds good.
Okay, thank you.
Okay. And I'll be around also the rest of the hour.
And I'm not shy. Good.
Hi, Doug. I wanted to talk with you a little bit about some deprecation issues on the software in the IDF a little bit, and
Oh,
and
okay.
some of the warnings about the new Python 3.11 that's come out.
Oh, okay. I'm not quite sure if I will if I'm the person to ask, but
Mhm.
I might be able to direct you to the right person if I can't answer it.
Okay, yeah, maybe the forum's a better place to post it, I guess. You know,
Yeah,
I was just running some some sklearn, a series of machine learning
mhm.
models on there, and the XG boosting wasn't working, and so I
Okay.
investigated it offline, and it looks like the um, the version that we're using right now in the IDF is has certain problems,
Oh, okay.
but that's okay. That's mostly if you're
Oh,
doing machine learning on like structured data that's all tabular. So
okay.
yeah.
Oh, I don't know. Melissa, do you think that's a breakout room worthy, or do you think others would be interested in?
I don't know if anybody would be interested. You know, it's hard to say.
Yeah, I'm gonna make 2 breakout rooms anyway, so you
Okay.
can pop
Oh,
in, chat, and just come back. It doesn't have to be
oh,
like a whole
all
topic.
right.
So,
Oh, Alan, if you, yeah, I'd be interested in seeing what the problem is. I don't promise I'd be able to answer anything. That'd be a little too deep into the code that I could answer, but I might be able to point you to the right person,
Cool.
or at least
That'd
to
be great.
Melissa.
Yeah.
yeah, it sounds like these questions might end up as GitHub issues. Like if it's anything about software capabilities, I think it might have to go to our SP team, but we'll see. We always do what we can first.
But yeah, let me take a, yeah, let me see what the errors are, and yeah.
Okay.
So let's see. Want to go to breakout room 1? And
Sure.
okay,
Terrific.
okay.
I'll see you over there.
See you in a minute.
Okay, so in that case, we hang out in the main room. We're here to answer any and all questions. I'm gonna stop sharing my screen. If you happen to ask a question and we get deep into conversation, we'll switch to a breakout room. But otherwise, you're always welcome to just hang out here and keep working. Unmute when you have questions. Very Stat Club like co-working session from here out, since we don't have like specific breakout topics for today. So yeah, I'm here. Go ahead and work. Yeah, unmuted anytime. Christina, Christina Williams, are you nearby?
I'm here.
Are here. So that confluence issue you were having, I just submitted a ticket for you.
Yes, I
Yeah.
saw I just got a communication from Ian Goodnow or Good Now, but I'm actually trying to reset my password now and it's not working. So
Still not working. Okay.
yeah.
Okay, if you, yeah, because I have the ticket here is open. So if you are trying to reset your password, if you have like specific error messages, I can put it in the ticket for you.
Well, I got the message from him that I should just sorry, now I forgot what his email said.
Oh, you have like a direct email with Ian?
Yes.
Oh,
Well, I
okay.
got one from a Jira. It looks like it's a Jira ticket. And then I got an email from him directly telling me that my account looks fine. So, but I just tried to reset my password again and it didn't work. So,
Okay, but if you have a direct email to Ian, then I don't need to like post updates
oh,
on the ticket. You could just.
no, I was about to write him back actually. So I can just communicate with him and see if I could sort it out. But thank you for submitting the ticket for me.
Okay, no problem. Good luck.
Christina, I know that there's a special way to do the password reset. It's not quite as straightforward as I can probably post you the link. I had the same problem some time ago, and I was told that I'm supposed to use something that goes like https pwd reset.lsst.org/pwm. I don't know if that's what you have.
No, I was just clicking the link that they tell you should click on the page when you want to reset your password. So I
You can give it a try. You can then
okay. Thank
post it
you.
in the chat window. Okay, is that what you're doing or something different?
No, that is not the page I was going to, but this page is telling me that the page can't be found.
Oh,
Sorry.
sorry to hear that.
Oh yeah, I get a 404 from that link is also Greg. They might not, maybe they don't use it anymore.
I think I used it maybe about a month ago or 2 months ago or something. You're probably right. Sorry for the confusion here.
Oh, no, it's always good to try stuff. Yeah.